Okay. Yeah, let's revisit this cell. So, in this cell, this is there is an inverter, and then I have a NMOS source follower at the VDD side, and PMOS source follower at the VSS side. So, the inverter supply voltage is limited in both sides, right? So, see, this is a triple N-well process, so I can connect source and bulk together. Yeah, source and bulk together. Then, so the threshold voltage are the same. This NMOS transistor must be same as this NMOS transistor, right? W of L must match each other. This PMOS transistor must match this PMOS transistor, okay? And then if the threshold voltage are the same, the logic threshold voltage will be just 1/2 VG1 plus VG2, okay? VG4. Independent of PVT variation, right? We've seen that, right? So let's connect this VG1 to VDD for simplicity, which is the largest voltage available, the highest voltage. VG4 to VSS. Then this is the largest voltage available for this inverter, right? We can reduce this VG1, we can increase this VG4, then we can set the GM and the current and the GM of this inverter. Oh, do I have okay, yeah, here. Let's look at this netlist first. Yeah, you can see the simple netlist here. Let's just see. Yeah, this simple netlist. I have a NMOS source follower. VGP is actually VG1. This is inverter. Inverter is 3x1, 1x1. This is a PMOS source follower. VGM is my VG4. Okay, this is VG1. So, yeah, I just apply input to this inverter. Okay, input. Let's see. Do I have some capacitor coupling? This is I1, right? Oh yeah. So there is yeah. This is I1 is just inverter, I1 O1. Okay. So those are this VG1, which is VDD. This is VG4. Okay. So we just look at the DC transfer curve of this one. Yeah, this thing is the one. So you'll see the same netlist here. Input, I will sweep input from 0 to VDD and see what happens. Okay, I change input, then what's the output? This is the one inside internal node. Right? You can see this one is from X1 XP node in subcircuit X1. Okay. So see here, let's just see. This red one is output voltage. It's the swing is reduced significantly, right? Because of those source follower. I used N-well CMOS. So PMOS bulk is connected to source. NMOS bulk is connected to VSS for all the cases. So this is only 2.1 volt here out of 3.3. 1.2 volt drop there. So here, let's just see. This is This is 0.6 volt here. So I have a 1.5 volt swing there. Only half, right? So those one, this blue one is that internal node. This magenta one is the upper internal node. Okay, my swing is severely limited, especially in the upper side. 1.2 volt drop here, and then 0.6 volt drop on the bottom side, okay? Yeah, logic threshold is what? Logic threshold is around here. Is it around half of VDD? No, 1.37 because of mismatch in threshold voltage, okay? Question?
틴셀에서요, UCX, LW가 서로 같지 않으면은 PVT 베리에이션이 남아있지 않을까요?
No, the question is, you say NMOS mu Cox W of L and PMOS mu Cox W of L. If there are some, yeah, they are different, right? NMOS mobility is different from PMOS mobility. But however, that part is compensated, you know. You know, because of this source follower, you've seen it before, right? Because of this source follower, that part is, you can see, you know, if they all they work in a saturation region, I1 equal some Kp prime, what was that? Is this VDD, VG1, oh sorry, VG1 minus Vin minus some NMOS threshold, yeah, VTHN1, which is a threshold voltage of this thing, and PMOS threshold voltage of 2 square, and then I2, this one equal Kp prime V in minus VG4 minus VTH N3 threshold voltage of this thing, and then threshold voltage of this one and square. So that Kp prime is the common factor, which is Kn times Kp square root Kn plus square root Kp square or something like that. So my Kn equal half mu n Cox W over Ln or something like that, okay? So they are saying, you know, at the logic threshold, you know, at the logic threshold, in a logic threshold, my Vin should be logic threshold, right? Then at the logic threshold, those two current are the same, so there is no current going out. That's a logic threshold, right? In that case, see, you know, those terms are cancelled out in this equation.
KP 프라임이 다른
You know, they are cancelled, right? So you mean mismatch? Yeah, that mismatch is a problem. But you know, the common change like mobility change or something like that, that's cancelled by this equation. However, if you have a mismatch, NMOS channel length has some mismatch, some variation with the PMOS channel length, then it still remains. Mismatch problem remains. But temperature variation is cancelled. Okay? The mismatch is, this is different from that one, right? Is this true? Or maybe not. Oh, actually, those Kp came from, this upper Kp came from those two transistors, right? Yeah, this Kp prime came from those two transistors. If there is a mismatch between this thing and that thing, it's a problem. It is different from each other, right? Yeah. Mismatch still concerns. Okay? Yeah, let's continue with the inverter-based bandpass filter. Yeah, they used that chin cell for this transconductor. Yeah, this is only inverter. You know, this thing is inverter. Yeah, the only thing is available is inverter. That inverter, right? The strange inverter. This is MOS. This is PMOS. This is MOS. This is PMOS, right? Yeah, this inverter. This is in, out. This is VG1, VG4, something like that. So we have an inverter only. So this one is bandpass filter implementation using inverters. Okay. So all those things are inverters. You can see, yeah, there is a capacitor. Yeah, this is a GMC integrator, right? GMC integrator. And then, yeah, actually this is a resistor. Okay, resistor. So it's a kind of a low pass filter, but there is one integrator here. See, we want to consider loop. Oh, this is a loop. Oh, somehow there is a small loop there. Let's compare this one with the other topology. Oops, not yet. Yeah, this is the bandpass filter implementation of using inverters. Yeah, this is the conventional topology for bandpass filter we've seen before. So let's look at the loop. We know this one is just a resistor, right? This is just a resistor connected here, one of GMC grounded resistor. So, you know, this part is a low pass filter. Yeah, this is a transconductor, differential transconductor. So this part is an integrator. I have one low pass filter and then see integrator. So this is a negative feedback, right? Because of this minus input. So by using the loop of one inductor and one low pass filter, we can implement a second order filter, right? So if we apply input here and then take output there, it is a bandpass filter. So let's compare this version with the upper version, the inverter implementation. Let's see. Yeah, so we want to compare loop only, okay? Loop. Where is this GM2 correspond to? Where is the corresponding part of, okay, integrator. Let's look at the simple thing. This minus GM4, inverting integrator, right? Inverting integrator. Where is the inverting integrator? In the upper circuit. Oh, looks like this is inverting integrator. If Vin is 0. Okay. Yeah, that's an inverting integrator. Fine. And then see this forms an inverting integrator with this. And then where is this non-inverting low pass filter? So I need a non-inverting low pass filter, right? Oh yeah. I have actually this is inverting low pass filter, right? Because of a negative sign. I can implement only inverting version because I can use only inverter here, okay? Inverting integrator or inverting low pass filter. So I need a polarity converter here, right? Polarity converter. So that polarity converter is implemented by this. You know, this, let's just say, yeah. I have this GM4 inverter, and then I connect this thing into here, the same thing, GM4 equals GM6, right? Then, you know, voltage gain from here to here is only -1, okay? -1. So I have an inverting low-pass filter, and then I have a polarity inverter. Then this entire thing, this entire circuit is a non-inverting integrator here, okay? Non-inverting integrator. So it is the same loop, right? However, I have one strange thing here. What is this thing? GM3. What is that GM3 for? Yeah, this GM3 thing is actually, let's just say, it should be same. I mean, GM3 should be same as GM4. You know, see, you know, if this is a V out, this should be minus V out, right? Because of polarity inverter. So if there is this minus inverter, see, you know, I can partly cancel this GM5. Yeah, so you know, the grounded resistor here should be GM5 minus GM3, right? Something like that. Okay. It is true. Yeah. See, because let's just say, you know, yeah, I will go forward. Yeah, for this thing, you know, current, look at this is a V out, right? And then this is 0. Actually, this is just inverter, just inverter. Okay, because of this minus sign, minus input, this GM5 V out will flows in, okay? And then because this is a minus V out, because of GM4 and GM6, this polarity inverter, then because this minus, right? Current must flows in, okay? It is true. Let's see. Yeah. This is V out. So, you know, this is a negative sign. So this current will GM3 times minus V out will flows in. So this is this I equals 0, and then this current will be plus GM3 V out, right? Then what's the current going through here? Oh no, what's current? Okay, what's current going through there? Yeah, this current is only GM5 V out minus GM3 V out, right? So this is GM5 minus GM3 V out. So it's the same as I am connecting a resistor here, resistor there, whose resistance is this GM5 minus GM3, okay? So the effect of this inverter, input output connected, and this feedback inverter is just this one, right? You can adjust. If you derive the transfer function from here to here, you will see it is a band pass filter. Question? No?